and thank you for the invitation to come and talk. So I'm gonna be talking about astronomy, but my specialty is the development of artificial intelligence for doing astronomy, and I'll explain why that's become extremely important, and why it's not a bad thing. But before I move on to the astronomy, I thought I'd take a poll of the room and ask everyone here, how many people are using AI daily in their lives? Okay. Either. Okay, so yeah, so I would say more than 50% of people put their hands up there. Right, yeah. So I asked this question at the beginning of all my talks, and the percentage of the room has been increasing every time I ask the question. So for those of you who didn't put your hand up, I'd say you probably are and you don't know it. So just some of the places where AI is creeping into our everyday life. So anyone who has anything voice activated these days, that's got a language model underlying it, as well as voice recognition software. So Alexa, Siri, Google Home Assistants, anything that gives you recommendations, whether they're films or shopping recommendations, social media. I think I don't really even need to mention this one. Maps. Yeah, I mean, I live in Rusholme and I still use Google Maps to get here tonight. It's just become automatic, right? Does anyone recognize these ones?
Yeah.
Yes.
Yeah. Yeah. So these are AI assistants that help you write things, whether it's code or prose or, you know, your homework assignments if you're my undergraduate students. Yeah. These ones, anyone familiar with these? So these are healthcare AIs. Yeah. Are there any GPs in the room? No? Okay. So yeah, so you might not see them, but your GP probably is using one or two of these. So it's really, AI is really pervasive, right? It's in almost every aspect of our life. And you know, there are people who have very mixed opinions on whether that's a good thing. So I thought I would also pose this question about why. Why do we use AI in our daily lives? Anyone?
Asking my brother.
Yeah.
Yeah, makes life easier.
Efficiency, yeah. You don't have to have family members like getting smug about answering your questions. Yeah, yeah. Efficiency because it makes your life easier. Yeah. Right. Okay. And I think that's exactly how we should be using AI. I think that's the purpose of all beneficial technologies. But when we say that we want it to make our lives easier, we have to be a bit careful, because a lot of the AI that exists out there, especially the stuff that gets the big flashy headlines, is actually doing the creative things that we as people want to do, like creating art and writing books and, you know, things like that. And that's, if the AI is doing that, it means we don't have to, so we can do all of the grunt work, right? And so I love this quote from a blogger who said that she wanted AI to do her laundry and dishes, so that she can do art and writing, not have the AI do the art and writing and leave her to do the dishes. And I actually think that this is a sentiment that we should echo. Yeah, it's a sentiment that we should echo in scientific research. So I thought I'd talk a bit about scientific process and where the AI comes in, and really where we should be focusing on bringing the AI in my opinion. And I'm quite happy to have dissenters. So if people want to disagree with me, that's also fine. I'm a radio astronomer. So that's why there's a radio telescope here. I hope everyone recognizes this radio telescope. Yes. Okay, good. But I assume optical astronomers do the same kind of things. So you know, doing astrophysics is a process, right? You don't just, you know, point up at the sky and go, oh, paper. So you do some pre-planning, you schedule some observations. The data you get from your telescope is not perfect, especially if it's a radio telescope. You need to calibrate it to make it physically meaningful. Generally, if you're using radio telescopes, if you're using radio telescopes, you then have to do image formation. because radio telescopes don't take images natively. You have to process the data in order just to get an image. Once you've got an image, there's all kinds of stuff in there, not just the stuff that you want for your science. So you also have to extract the relevant information from the image. And then typically in modern astrophysics, a single observation on its own is not enough to derive a scientific result. You need to combine that observation with other data, possibly from other telescopes or from the same telescope on a different day. And then you need to perform a joint analysis. And that's where, you get your parameter constraints or your new model out. And that's your science result. And that's the thing you write about. So the question is then, what kind of AI comes in here? Well, I would say that this bit at the end and the science result is the most interesting bit. This is the art and literature bit, right? As a scientist, this is the bit that you want to do yourself. This is the bit you studied for. Everything else is kind of grunt work, but it's different types of grunt work. So just to be quite clear on that, if we take the calibration and the imaging, so these are processes that astronomers typically won't do by hand or by eye. They're done by a computer algorithm. So that computer algorithm might be really slow, and so AI could help you speed it up. So this would be an example of where AI is replacing a task that's already done by a computer. So it's not replacing a human task. However, if we then do the extract information from image, that's often still done by an astronomer, right? It requires an astronomer to actually look at the data and say, this is the interesting bit. And that's where, all of your experience with other astronomy data helps you to do that. So if we put AI in here to extract information from our image, that's where the AI is replacing something that a human does. So these are two different types of AI. And mostly what I'm going to talk about tonight is this one. So how AI is doing what humans does. The AI that's used to replace things that computers does is generally called surrogate AI. And it's just used to speed things up rather than to, imitate people in some way. So a lot of the motivation for the work that I've done over the last almost a decade in this field, sorry for the slightly jerky video, has been done as part of the development for a new radio telescope that we're building called the Square Kilometre Array. Now, again, Lovell telescope here. If you go to Jodrell Bank these days, you can, of course, still see the Lovell telescope in all its glory. And you can go to the Visitors Centre, the new First Light Pavilion, unashamed plug. But you'll also notice that there is a new shiny building on site that you can't visit. It's not part of the public area. And that building, it sits at the bottom of the dish. So for those of you who know Jodrell Bank, the Visitor Centre entrance is over here. This is the old observatory building here. And then this is the new building here. And this is the global headquarters of the Square Kilometre Array Observatory. It is an intergovernmental organisation. It's a treaty organisation. It's technically not part of the UK. Quite fun. Right? It does not have a duty-free.
Oh.
Yeah, because if you have a duty-free, you have to have a customs post.
Oh.
Yeah, things you learn, right? But yeah, it's like CERN, but for astronomy, for radio astronomy. It's the first intergovernmental organisation in the world ever for radio astronomy. So it's a big deal. Yeah, and it's a big deal that's in the UK and that it's in the Northwest. And it's going to be the headquarters, the global headquarters for the next 50 years. So it's a significant investment. And what it's doing is building, is that going to play automatically? Okay. It's building two telescopes, in fact. The first of these is what you might traditionally think of when you think of a radio telescope, which is dishes, right? It's lots of dishes. This is a centimetre wave radio telescope. It's called the Square Kilometre Array Mid-Frequency Array. There will be 197 dishes. There are 64 already in place. And it's located in the northern Cape of South Africa, in the Karoo region. It's a semi-arid region. And that forms the first telescope of the SKA. The second telescope is a very low frequency radio telescope. So this works at meter wavelengths. If anyone's seen the LOFAR telescope in the Netherlands, this works in a very similar principle. So at very long wavelengths in the radio, you don't need a solid dish to reflect the radio waves. You can collect them with what are essentially television antennas. And you can think of each one of these stations, these clusters of antennas, as being equivalent to a dish. And so there are going to be 150,000, I think, of these dipoles. You'll notice the terrain in the background looks very different. This is in Western Australia, in Murchisonshire, which is a much better location for very low frequency radio astronomy. The key thing that connects the Northern Cape of South Africa and Murchisonshire is population density. So Murchisonshire is an area of about 50,000 square kilometres. That's about the same size as the Netherlands. There are 110 people who live there. Yeah. And no radio, right? No man-made interference, which is the thing that we're trying to avoid. Okay, so I'm not going to talk about the technical details of the telescopes very much, but what I will say is that as well as being cutting-edge scientific instruments, they're also big data machines, because the more antennas you have and the higher the rate of digitization you have, which is very good now, then the more data you collect. If we stored all of the data that was received by the low frequency antennas in Western Australia, we would be storing about 5 zettabytes of data per year. Is everyone comfortable with a zettabyte?
No.
So,
It sounds a lot.
it is a lot. So a zettabyte, so a gigabyte is 10 to the power 9 bytes. A zettabyte is 10 to the power 21. So it's a huge amount of data. We don't store all of that data because that would be ridiculous, right? I mean, scientifically it'd be wonderful in principle because of all the information it contains. In practice, it would be a nightmare because it would cost a vast amount of money, and we wouldn't be able to process it anyway because it's too much data. So we compress down the data from both telescopes to a mere 600 petabytes per year. So that's 10 to the 15 peta, which is still a lot of data, right? This is a lot of data. And I realize that I say petabyte and I say zettabyte, and they're very difficult to put in context. So I wanted to clarify how big a petabyte is. And the answer is that it's basically about 3.5 years of your life. So if you recorded every second of your life 24/7 in HD, that would be about a petabyte, that video. And there's some equivalents here. So your brain is thought to store about 2.5 petabytes, or 4,000 digital photos per day, every day for your entire life would be about a petabyte. So even on its own, right, it's a lot of data. And the reason we take that data is because the universe is a very large and interesting place. And if we want to do the deepest science that we can, the more data we have, the more science we can extract. And this is a balancing act, right? 600 petabytes is a lot of data, but we can just about cope with it. But we have sacrificed some science by compressing our data to that amount. However, we still need to deal with that 600 petabytes. And that means automating a lot of our processing. So a lot of the things that historically we've done by eye or done by hand, you just can't do them with that volume of data. And that includes a lot of the things that you know, I would do personally or my students would do personally. So the interest in using artificial intelligence for astrophysics has increased massively over the last decade. This is just a figure showing you the increase in the number of publications in the astronomy literature that use the words AI, deep learning, or machine learning in the abstract or title. And these are not all radio astronomy papers, because the SKA is not the only telescope that's recording these kinds of data volumes. So lots of telescopes are now recording huge volumes of data, and everyone needs that level of automation in order to do their science, you know, before they retire, or before the government cuts the funding because they're not seeing any of the science out that they paid for. So let me give you an example of how this kind of thing is done. So this is an image, a radio image. I forget exactly how big it is. I think it's about 1.5 degrees on the sky, taken with the Meerkat telescope in South Africa. Now, Meerkat is the first 64 dishes of the SKA mid-frequency array in the Northern Cape of South Africa. And for those of you who are not familiar with radio images, basically every bright spot that you can see in this image is a supermassive black hole. And as you can see, there are lots of them, right? And they're not all the same, is the complication. So typically these days, to study the evolution of black hole growth, of galaxy formation, of galaxy evolution, because that's what these black holes are driving, we will extract out large samples of these black holes from our survey images and do a statistical analysis that uses those data. But we need to know which ones are which. We need to know what types they are. And one of the ways that we separate them out is to use their morphology, i.e. the shape that they have in the image. So what you might notice, if you stare long enough at this image, is that in fact most of the dots are not single dots. They tend to be clustered, so you'll see 2 bright points close together. And I've highlighted one down here that's quite clear. And what you're actually seeing, in fact, let me switch to the next slide because I think it's shown. It's not just the black hole itself, which is the thing in the center here, but you're seeing these 2 patches of radio emission on either side of the black hole. And this is because the black hole is accreting material onto itself. And in order to conserve angular momentum, it then has to eject material. And it does that through the formation of 2 jets of material, which are moving at relativistic speed, so close to the speed of light. And then they basically slam into the surrounding intergalactic medium, and you get these shocks at the end. And that's what you're seeing here, these bright regions. Now, if you asked a radio astronomer what this was, they would look at it and tell you that this is a Phaneroff-Rayleigh class 2 radio galaxy, which is a particular type of black hole. The distinction being that it is not a Phaneroff-Rayleigh class 1 radio galaxy, which looks like this. And the difference you can see by eye is that in the class 1, in fact, you don't see these big shocks at the end. You see this kind of smoke-like jet coming out. And it's much brighter, closer towards the central supermassive black hole. And this is a difference in the types of black holes, or radio galaxies is what we typically call them, that we've known about since the 1970s. And we don't know why. Originally, it was just thought to be a difference in the power of the black hole itself. So the class 2s were thought to have more powerful black holes at their centers, and the class 1s, weaker black holes, you know. But then as we've got more and more sensitive data, what we're seeing is that's not the case. So this is a scatter plot just showing you the distribution of data on these kinds of radio galaxies from the LOFAR telescope, which is a radio telescope in the Netherlands. And the yellow points are the class 1s, and the blue points are the class 2s. And if it was the case that it was just that the class 2s were always more powerful, they would all sit above this dashed line. And the yellow points would all sit below the dashed line. But in fact, what you can see is that there's some crossover, right? So it's not just about the power of the black hole. And there's a number of other factors that could be affecting it. Could be something else about the black hole. So the accretion mode, so how it's accreting material, the dynamics of the jet. It's not necessarily intrinsic to the black hole. Could be something about where the black hole lives in the universe. It could be environmental. Or it could be something to do with a difference in the composition of the jets. Now, we do have some questions still remaining about what's in the jets. So typically, we think they're made up of electrons and positrons, but it's possible there are some protons in there. They're highly dissociated material because of the energies involved. But then they tend to, as you can think of like a jet of air, right? It will entrain material from its surroundings as it moves through, whatever it's moving through. That happens with these jets as well. So that could also be a factor. And the only way we're going to disentangle this is to get larger and larger samples that allow us to systematically test each of these things. And that means extracting more and more of these black holes or these radio galaxies from these big radio images. Now, historically, we've done that by eye. So literally, an astronomer has sat down and said, this one's class 1, this one's class 2. Well, they've got their PhD students. Their PhD students have sat down and said, this one's class 1 and this one's class 2. Because that was possible. So in the 1990s, you had about 50 to 100 radio galaxies in every square degree of a radio survey. LOFAR, the data that I showed you on the previous slide, they're finding about 1,000 sources per square degree. It's just about doable. But with the Meerkat telescope and ASCAP, which is its Australian equivalent, we're going up to a few thousand. And with the SKA, you're talking 100,000 to 1 million sources per square degree, right? And so, as a colleague of mine likes to say, there might be enough graduate students in the world, but there probably isn't enough coffee. So the way we've done this historically just doesn't scale. And in fact, my students took some pictures of radio galaxies around our department and worked out how long it takes people to actually decide. Because, not all of them look as nice as the canonical images I showed you in the previous slide. They look more like this little zoo of radio galaxies over here. So if you had an expert radio astronomer looking at these sources all day, every day as their entire job, they'd be able to do about 100,000 sources in a year. Right? Citizen science was thought to potentially be a solution, but if you have someone who's less expert, then you need more people to agree on a single source. So you need more people to agree. And even if you're doing this with expert astronomers, you probably want 5 or 6 people to agree on each source. So that also doesn't scale just in terms of the number of sources. And then you bring along a machine learning algorithm that can in principle classify 100 million sources in 15 minutes. And I mean, right, there's no argument. Yeah. Or is there? Which is actually what a lot of my work is about, is how you make sure that your machine learning is as robust as your human astronomers. So what the machine learning allows us to do, even at this point, is to go from the LOFAR data, which has about 1,000 sources in it, to something that looks like this, which has about 30,000 sources in it in about a minute. And this is what our own AI algorithms have currently done with existing radio surveys. So how do we do this? Now, I'm not going to talk about all of deep learning and all of AI. It's a whole thing, right? You could talk about it forever. I'm going to tell you about how our group is doing it, and then about some of the advantages and disadvantages, if you like. So most of the data that we have in astronomy doesn't have any labels with it. So when I say labels, right, I mean, we get some data and we don't know what's in it. Right. Now, that's different to a lot of commercial artificial intelligence. A lot of commercial artificial intelligence is built on data sets where someone has actually already said what's in the image. And they might have said it knowingly by, physically saying this is a cat picture and this is a dog picture. Or they might have just written a caption on Facebook saying, this is my cat. And, Meta have gone away and labeled image cat. So you can't use traditional AI methods that are used commercially because you just don't have that same degree of labeling. And this is always going to be a problem for astronomy, because astronomy is actually quite unique in the physical sciences in that you never control the experiment, right? You can only ever observe what's happened somewhere else. I can't go away and twist my radio galaxy around to see it from another angle. Can't change the power of the black hole and see if that changes the jets. Right, we're always inferring what might be happening just from the data, which is different to a lot of other physics where you actually set up an experiment and then look at what comes out the other end. So if you have that kind of data, the kind of artificial intelligence that you tend to use is something called self-supervised learning, which means that you don't know what's in your data. And typically what you learn are patterns. So I'll take two images and my model will try to learn which ones are similar to each other. So for example, if I had a database of pictures of cats and dogs, it would try to learn to put all the cats on one side and all the dogs on the other side. But it wouldn't know what a cat or a dog was. It just knows that all of these ones look alike and all of those ones look alike. And that kind of similarity matrix, if you like, is generally referred to as a foundation model in artificial intelligence. And the actual physical encoding that it produces is called a latent representation. And then you can use that directly. So say I get a new photo, my mum takes a photo and I want to know, is this a cat or a dog? I can put it through that model, and depending on which cluster it ends up in, I can say, well, it's in this cluster and the other images in that cluster look like a cat, so my new photo is a cat. That's a similarity search. So those kinds of tasks. But then the other really important thing you can do with it in astrophysics is that you can take that self-supervised model and you can do a process called fine-tuning. And fine-tuning is where you then use a very small data set of labeled examples to actually teach the foundation how to answer a specific question. So for example, I could take that similarity model and then take 10 images of cats and dogs and teach it to learn that these ones are cats and these ones are dogs, not just that these ones are similar and these ones are similar. And then I can use it to answer that specific question. So for my radio galaxies, I could take 100,000 images of radio galaxies, random images, learn a similarity distribution, and then take 100 labeled examples, historical examples, and teach it to tell me which ones are which. And so that's what we're doing. That's how we're building our models. And it's also how the commercial AI companies are now starting to build their models, mainly because they've run out of labeled data. And at this point, actually, they've run out of unlabeled data. So we'll see what happens next. So are people familiar with these two acronyms? Yeah, so GPT, so we're actually on GPT-4 now. So GPT is the foundation model for language that underlies the ChatGPT service. DALL-E is a foundation model that jointly works on images and text. So you can ask it to create an image based on a text description. So these are different types of foundation models. This one just uses text data, and this one uses image and text data. So we're doing the same kind of thing that these models do, but we're doing it with astronomical data. Oh, I just threw this in. So, I mean, I asked ChatGPT what she put in the talk about AI and astrophysics, and it gave me a list, and it sounds quite coherent. There are no specific details, which is not helpful. And actually, I've ignored it completely. Okay, it's running already. So our foundation model, our similarity matrix for radio galaxies, looks like this. If I just show you a cloud of points. Now you can see it's not as simple as two clusters, right? It's not cats and dogs. What you can see is that there's like this web of data. So every dot in there is the encoding of a particular radio galaxy. So there's about 170,000 radio galaxies in here. And what the animation is showing you is that when my student Inigo, who built this model, clicks on one of these dots, that's what the little red cross is, it'll show you that galaxy and then the closest galaxies to it in that representation. So that's how we do a similarity search. And what we've been able to do with this is we've been able to take a very rare type of radio galaxy called a hybrid radio galaxy. So this is one that has characteristics of both class 1 and class 2 on different sides. So you can see this is the class 1 woofly jet. This is the class 2 jet with the shock at the end. So this galaxy wasn't in the data we used to create our model. It's completely separate. image, we encoded it through our model to see where it ends up in that distribution, that web of points. And then we found the most similar other galaxies to it. And what it's given us back, so I'm just showing you 8 here, all of these are hybrid radio galaxies. And this is really important because there is no systematic way to search for hybrid radio galaxies in radio surveys at the moment. So in fact, we managed to create the largest sample of hybrid radio galaxies that's ever been made, which is incredibly important because in evolutionary terms, these galaxies are telling us something very specific because they don't fit into one of the 2 classes. So that's a direct way we've been able to use this model. The other way we can use it is to do that fine-tuning technique. So here we've actually fine-tuned the model to directly tell us whether a new image is a class 1 or a class 2 radio galaxy. And we did that by taking our similarity representation, the blue points, and then fine-tuning it using a small set of labeled data, which is the orange points. So as I said, there are about 170,000 blue points, and then there's about 1,000 orange points. And that allows us to improve the margin on a direct classification model significantly. That's what the figure on the right is showing you. So again, one of my colleagues likes to describe this as the blue points are giving you context to your question. So if you think about it in terms of learning a musical instrument, the first time you learn a musical instrument, it's really difficult, right? There's a very steep learning curve. You have to learn lots of new things. But if you go and learn a second musical instrument, you already have some context from the first musical instrument. You know the general principles around it. And if you learn a third, it becomes incrementally more easy again. And that's exactly what the similarity representation is doing. It's providing that context. It's your first musical instrument, so that when you then ask it a specific question, it has a better understanding of the general premise around the question than if you just ask the question directly, which is pretty amazing. So, as I said, I'm a radio astronomer. I don't do much optical astronomy, but one of the things that my group, and particularly my postdoc, Mike Wormsley, worked on is actually doing the AI that underlies the Galaxy Zoo project. So I don't know if there are any users of Galaxy Zoo in here. You might actually have participated in some of our tests if you are Galaxy Zoo users. Does anyone not know what Galaxy Zoo is? So Galaxy Zoo is a citizen science project for astronomy. So if you want to come and look at some pictures of galaxies and help us understand what they are, it's a very simple web interface. You can even do it on your phone, and it will show you a picture of a galaxy and it will ask you questions like, is this a spiral? Is it a clockwise spiral? Is it an anti-clockwise spiral? Does it have a bulge in the middle? And there are helpful explainers for all of these things if you're unsure about it. And it's been hugely successful. So I think Galaxy Zoo volunteers have now classified millions of galaxies. These are the kind of images that you get shown. So this is just a little montage of different types of images. But as I said, we now have more galaxies than we can actually cope with just in Galaxy Zoo. And so we built a foundation model for Galaxy Zoo. And this is Mike's work. So instead of showing you just like a cloud of points here, what we've done is we've actually represented what the points in different areas of our similarity matrix look like. So you can see that you've got some spiral galaxies over here, some edge-ons over here, got some elliptical blobs up here. And this was built using the Galaxy Zoo decals dataset for any of you pro Galaxy Zoo people, which has about 300,000 galaxies. And it was built using the answers that the Galaxy Zoo volunteers provided. So there were 206 questions in total in Galaxy Zoo. And we built a general representation based on those responses. And then we used it to answer new questions that weren't asked to the volunteers. So I think maybe I've got this on the next slide. So one of the questions we asked it was, is this a ring galaxy? So the original Galaxy Zoo interface didn't ask the citizen scientists, does this galaxy have a ring around it? So when I say a ring galaxy, this is an example of a ring galaxy. So it's not really a spiral, it's just got a ring of star formation around a central galaxy. And by fine-tuning the Galaxy Zoo similarity model, the foundation model, using a small number of ring galaxies, we were able to discover 30,000 new ring galaxies that weren't known about before, which the press loved. They called it a cyborg collaboration. But also, again, it was very astrophysically important because these ring galaxies, so they're super rare. Before this sample, there were about 100 of them identified, just because they're really difficult to pick out. There aren't very many of them. And it turns out that, so I don't know, so spiral galaxies like our Milky Way, they tend to be quite blue in optical images. There's lots of active star formation going on. They're quite young. They're doing stuff. And then at the other end of the spectrum, you have your elliptical galaxies, which are red in the optical. We call them red and dead. There's not very much active star formation. They're basically at the end of their lives. And then there's this gap in the middle. And it turns out that all of these ring galaxies sit in that gap. It's called the Green Valley. And they have very green optical colors. You can't see that from these images, but they have very green optical colors. And they're basically showing us the evolutionary track between spirals and elliptical galaxies. So they're incredibly important. And in fact, the way we measure that evolution in our models is to count the number of galaxies of different colors. So having this large sample of ring galaxies is really important. Okay. So this is my final slide, really, because I think I've been talking for a while. So I think I've hopefully highlighted some of the benefits of using AI in astrophysics research, but it does have caveats. And in fact, whilst I've shown you the astronomy highlights, most of our time is spent identifying the problems in AI algorithms. So identifying the biases and understanding the uncertainties that are associated with the predictions that the AI models make. And it's very easy to become trapped in an AI bubble where you just believe everything that the AI tells you. And anyone who's played with ChatGPT extensively knows that ChatGPT will make things up. And that's fine if you're using it to, I don't know, draft an email. But it's not fine if you're using it to constrain the parameters of galaxy evolution. So we have to be a bit careful, or very careful, in fact. And that's where I'll finish. So thank you very much, and I'm happy to take questions.
I've heard these, been to these lectures with the square kilometre array and the big 38 metre telescope in Chile. And I think what I remember the speakers saying was that there's so much data that's generated by both systems that the data is actually split up into about 7 different universities, research institutes. Is that the case, is it?
Yeah, so in fact, so for the SKA, that 600 petabytes, in principle, there'll be 300 petabytes stored in Australia and 300 stored in South Africa. But then with that kind of data volume, you can't just log in with your laptop and start working on it in South Africa. It doesn't work. So the plan is to have a series of data centers around the world that keep a copy of the data. So we've got redundancy if anything goes wrong. And so for Europe, there is a current effort to build that data center at the moment. And that requires not just the storage for the data, but also the computing for the data in the same location, so you don't have to keep moving the data around. Yeah.
I was just wondering about the data compression that you mentioned, and it sounds kind of analogous to music. And when you compress music, you lose the quality of the audio. And I wondered how you take care of not potentially throwing good data away during the compression.
Yeah, so I mean, it's a really good question. So the way we compress our data is different to how you'd compress music data, because of what we want out of the data. So for example, when you compress music data, you generally compress it in a way that removes background noise and things like that. We can't do that because our data is essentially noise. And it's only when we put a lot of it together that we see the signal. So our compression comes from changing the representation of the data. So for example, going from the raw data to an image will generally compress the data, but you do lose some information. So you'd lose some of the time resolution, you lose some frequency resolution, and you lose some of the science. But unfortunately, we're just in a situation where we have to do that, right? You have to balance the importance of the science against the responsibility of trying to keep the data if you can't do anything with it. Yeah.
Forgot all my questions. I had a couple of questions. One was, you said that Jodrell Bank Centre for Astrophysics is going to be the HQ of the SQA for the next couple of years. Is that what you said?
So the headquarters of the SKA is based at Jodrell Bank, but it's a separate organisation. So Jodrell Bank Observatory is owned by the University of Manchester, and they are playing host to the Square Kilometre Array Observatory, which is its own entity. But the agreement is for 50 years.
50. So it's going to stay in Manchester for 50 years.
Yeah.
Yay. Brilliant.
Yeah.
Brilliant. That's
Yeah.
lovely. Yeah.
I believe it's also the only treaty not just the only treaty organisation for astrophysics, but it's the only treaty organisation in the Northwest. Yeah.
You got a question?
In terms of the ring galaxies that you
Mm.
found, were they already in the Galaxy Zoo? Because I don't remember ever seeing a ring image.
Yeah, no,
pop
they
up
were
on
already there, but you weren't asked the right questions. Yeah.
So you
yeah,
just
it's-
asked about the spiral arms, whether it's barred, whether it's
Exactly.
bulged,
Yeah. So
whether it was edge on, but they never actually said, did it have a ring?
Exactly. And in fact, the idea for looking for them came from the comments. So if you use Galaxy Zoo, you can write a comment about the galaxies. So there are some galaxies in there where people wrote, this looks like a ring.
Or
And there
this
was actually a
bit blue,
hashtag
or this
ring
was a
or-
bit
yeah.
green, or
Exactly.
yeah.
Yeah.
Wow, that's cool. I
Yeah.
never thought
That's
of
really
that.
cool.
You mentioned about how the AIs are going to be doing some of the work that was previously done by citizen science, but you also mentioned that there are issues with the AI possibly not getting things wrong. Will there be new citizen science projects looking at those mistakes, trying to identify whether the AI is getting anything wrong?
Yeah, definitely. So I think, so it's not going to replace the citizen science. They will work in parallel together. And in fact, if you log into Galaxy Zoo now, the galaxy that you're shown is actually determined by our model. So Galaxy Zoo will preferentially show you the galaxies that are most scientifically useful, as determined by our model. And we do that to improve the model. So it's for exactly that reason. Yeah.
Does that mean that you're looking at the edges of your model more than the center?
The intersections.
Yeah.
Yeah.
So where you
Yeah, exactly. So you can more cleanly separate the overlaps by oversampling the galaxies that sit closer to those overlaps. Yeah. Yeah.
Yeah, what are you hoping to find out about galaxies and galaxy evolution through all this? It sounds like galaxies start off as spiral and then go to ring galaxies and then die as the elliptical galaxies. Or do you hope to find out more about cosmology and or what?
Yeah. So I may have somewhat oversimplified things. So there's a whole host of questions, so the spiral galaxies that I showed you, typically, those ones don't have such massive black holes as we see in the radio galaxies with the giant jets, although there are some contradictory examples. For my research, what we really want to know about is how the black holes are born and how they evolve. And there's loads of questions there about, what relates to the black hole itself, what relates to its local environment, what relates to feedback from the galaxy around it. And then for the spiral to elliptical evolution, I know less about it, but I do know that they don't know exactly how it works yet, right? I think we know a lot of the sweeping statements, but then when you get down to the details, there are lots of contradictions. And one of the interesting things about new surveys is that you always find out something that contradicts something you thought you previously knew, which is just a natural part of a science where, like I said, you don't control the experiment, right? You never have the full picture. You're always trying to infer the answers from the details.
So it's sort of like the more data, the more there is to build your theories on, and so
Yeah.
go back and get more data to test that sort of thing.
Exactly. So I mean, there are some so for the square kilometre array, I should say that the telescopes have been designed to optimize for some very specific questions. So one of them is, when did the first galaxies form? So we know the age of the universe, we know about the cosmic microwave background, and we know that after the cosmic microwave background, there was this period called the Dark Ages where the universe was basically just neutral hydrogen. But then at some point, within a certain range of time, the first stars and galaxies were born, and they started to ionize the hydrogen. They started to release the electrons from the hydrogen atoms. And that ionization was the seed of growing those galaxies that we see around us today, because at that point, what a star looked like was very different to what a star looks like today. So we know that happened. We have a range of cosmic history where we know it happened, but we don't know exactly when it happened, and we don't know exactly what the mechanism was. So there are three main competing theories, and we need to distinguish between those. Another big question is, where did the magnetic fields come from in space? So we know that wherever we look in the universe, we see magnetic fields, and they're really physically important. So star formation, for example, depends heavily on the local magnetic fields, both to trigger it and to slow it down. They play multiple roles. But we don't know if those magnetic fields are something whether they were born very early in the universe and then they basically got expanded through structure formation, or they might actually have been injected in by the action of black holes later in the universe. So we have these two competing models, and we have a prediction for what the magnetic field strength should be in certain areas of the universe for the two models, but we don't currently have the sensitivity to distinguish between them. So again, that's something the SKA is hoping to do. And to answer that question is literally about being able to detect enough black holes to probe that magnetic field structure in sufficient detail. Yeah.
Thank you.
Yeah. Well,
If I could please take you back to an earlier slide.
Yeah.
I don't know if I just wasn't concentrating at one point, but you had FR1 and FR2. Can you please explain that a little bit again? What was the FR for a start, please? What
okay.
was that?
So
What did it stand for?
FR stands for Faneroff-Riley.
Pardon?
Faneroff-Riley.
Is that a person?
Yeah, it's
Yeah,
two
two
people, in
people.
fact. So it's Bernie Faneroff and Julia Riley. So they were radio astronomy PhD students in Cambridge in 1974. And they were looking at one of the very earliest radio surveys. And they were trying to, so Bernie was doing the observational work, and he'd been like separating out these galaxies based on what they looked like. And Julia was doing the theoretical analysis. And together they came up with this line. So in the survey that they were looking at, which was significantly less sensitive than the one that provided this data, they found that all of the FR2s sat above this line and all of the FR1s sat below that line, which is really nice, right? It gives you a very clear division, says these ones are more luminous and therefore more powerful, and these ones are less luminous and therefore less powerful. And, you know, for a while, everyone thought, oh, they're sorted then. Until someone took a more sensitive radio survey and they started to see this overlap, because there were hints of this. This is quite new data, but there were hints of this overlap even back in the 1980s. So yeah, so the pictures they had did not look like this, right? They were blobs of different extensions.
Thank you. Oh, there's just one other thing.
Yeah.
Earlier on still, you had, it looked like the source was, it was a graph, and you had, there we are, ARXIV. I've never heard that word before. I wouldn't know how you pronounce it. What is it, please?
So people, it's called the archive.
Well, I thought it might be.
Yeah.
I don't.
So every astrophysics paper that's published in a journal, a peer-reviewed journal, also has a copy posted on an online server called the archive. And it's an open server, so anyone can read the paper.
Where's that hosted?
Archive.org.
No, but which country? Which
Oh,
country?
the US. It's hosted in the US.
Right.
Yeah, I think they have mirrors. There's an archive mirror in the UK. There's one in Switzerland. Yeah.
Got one further question,
Yeah.
if that's okay. Yeah.
Yes, one go.
I can save it till last if you want. Yeah. Right. The plan is to, because space is nice and cold, the plan is to start storing data in space. Yeah. Oh, thank you. To start storing data in space. That's not begun yet, has it really?
So so I haven't heard that, I have to say. So it's cold, but the infrastructure costs would be huge.
Mhm.
Also, getting this volume of data on an uplink stream to a satellite would be very difficult. It would take a long time. So typically, satellite missions are, the amount of data they record is bounded by the amount of data they can downlink to the ground, because those downlinks are not
Free.
they're not free, and they're not even that good, is the reality. So what you can do on a physical cable on the ground is just not possible
Oh, I know.
on a
yeah,
satellite
yeah,
downlink. Yeah. So uplinking data to space, you'd have the same problem. So I would not foresee that in the very near future, not for these kinds of volumes of data. If you had small volumes of sensitive data, that would make sense. Yeah.
Yeah, I think that was what was discussed at the
Yeah.
time. Right.
Anyone got you gonna have a check on Zoom? Anyone got another question in the room?
You know, when you spoke about your unstructured data and your labeling right at the start.
Yeah.
How did you begin with actually training it with the self-supervision to identify what classification the data would fall into? Was it just a binary pair to begin with, or?
The self-supervised, so in the self-supervised model, we initially don't train any classification.
You
So
just
we do,
give it the images and
we give it
say-
so there are two main forms of self-supervised learning. One is called mask-based self-supervised learning, where you basically mask out part of the image and then teach an algorithm to reconstruct it. It's also referred to as generative AI. And then the other form of self-supervised learning is something called view-based self-supervised learning. And that's where you give it an image and you give it the same image, but you like shift it slightly.
Yeah.
And then you teach the algorithm to map those two images to the same point in the representation, because essentially they're the same thing, so they should be optimally similar. We use view-based self-supervised learning, and it basically learns the similarity between different images. So if you assume that all of your class 1s are similar in some way, and all of your class 2s are similar in some way, but the two are separate, then that kind of algorithm should map them into distinct areas of your model. So we did that initially, just on similarity. It doesn't know anything about Fanneroff-Riley or any other kind of, I mean, it knows nothing about astrophysics at all, right? It knows, yeah, they could be cats and dogs for all the algorithm cares. And then we use a process called fine tuning, where we have a data set of about 1,000 labeled images that have been labeled by eye. Exactly. Yeah. Exactly. It basically shifts the thing. It doesn't just separate it into two clumps. It's quite interesting. Yeah. And one of the things you have to remember about this, which is,
and like you said before, sometimes it'll get them in the wrong category.
Yeah,
And you have to
yeah.
identify where it's gone. Oh, you put an FR1 in an FR2 class.
or you have to go back and say, is this what I thought it was? Right?
Yeah.
Because the classification itself is a human classification, right? It's a very subjective human interpretation of what is some very complicated underlying physical set of processes.
So did the label data get it right in the first place?
Yeah, exactly. Are the astronomers right? right? It's possible that the model will learn some pattern in the data that we haven't seen yet. And that would be really good. Yeah. And you can see this in stellar data. So there are AI models that have relearned the Hertzsprung-Russell diagram that classifies stars by stellar type.
Anywhere where you've got a gradiated.
Exactly, yeah. And they pull out like the dwarf stars and the red giants and stuff as well. Yeah, you know, things that took decades and hundreds of years for humans to learn. Yeah, yeah.
Anyone else?
I just noticed on your slide there, you said at the top, the SKA will be the world's largest radio observatory. What's the difference between that and this 38-meter one in Chile?
So I think the one you're talking about in Chile is the ALMA telescope, is that
Yeah,
correct?
the very large telescope we're talking about. What's the difference between that and?
So there are different ways of categorizing largest. So the SKA will be the largest in terms of the number of dishes and in terms of the collecting area. And when we talk about sensitivity of a radio telescope, the collecting area is the key thing. So it's the largest. It's the largest in terms of the number of dishes, the collecting area, the frequency range. What else? I don't know. Cost, maybe. Yeah. So yeah, it is. So one thing that I don't put on my slides, but is used by some people, is that by many measures, the SKA will not only be the world's largest radio observatory, but it will also be the world's largest scientific facility. Yeah. But then you have to be a bit careful because the particle physicists get very touchy about that.
Yeah. A high circle versus you stretching across the globe.
Exactly. Yeah.
And then you get the satellite ones going, well, we're even further than that.
Yes.
Jupiter now.
Exactly. Yeah.
Shan did ask a question. Shan, I don't know if you want to come off mute or I'll ask it for you. Mind you, she can't respond, so that's going to be an interesting one. She said, I wanted to ask about Galaxy Zoo and its potential to find new things like the ring galaxy that it found, and how we then go on to ask more questions and how new themes might emerge from that.
Yeah, so Galaxy Zoo is the most amazing resource. I really encourage everyone to get involved. So there are all kinds of, so it's a resource for new questions in two immediate different ways that come to me, since I haven't thought about this question a lot. So the first one is that having the data set in a curated form just on its own means that if we come up with a new scientific question, it's already ready and there to use. So that's very important. The second thing is that when you have so many citizen scientists looking at the data, they suggest things. And that starts to bring up themes. So like I said, the ring galaxies came from the comments. So if you are using Galaxy Zoo, don't just click yes or no to the questions, really. Just, you know, if something looks weird to you, say it looks weird. I mean, so the ring galaxies aren't the first thing. I don't know if anyone's heard of Hanny's Vorwerp. Right. I have to admit, I've forgotten exactly what it is, but it was a new thing that came from Galaxy Zoo very early on that was identified by a citizen scientist in the Netherlands, hence the name Vorwerp, which I think means green blob. Yeah. Yeah.
Any more questions? I've been stimulated.
Is AI able to offer explanations yet for things that it's found, or is that still a human's job?
Oh, so this is a good question. Yeah. At some level, so some of the work we've done has been on getting AI to identify the things in the image that caused it to make the prediction that it made, right? And certainly for the radio galaxies, what we were able to see was that the AI algorithm looks at the same regions of the radio galaxies that a radio astronomer would look at to make its decision. So we can see that. For other questions, it's more complicated. There's a whole field of AI called explainable AI, or XAI is what it's generally referred to, which is about how you can interpret the predictions made by AI algorithms. It is not very well developed. It's extremely, the techniques are extremely trivial compared to the complexity of the models at the moment. However, I think especially when you have a model embedded into some process, whether it's astronomy or medicine or the judicial system, for example, you need to be able to have that, right? Because an algorithm can't take responsibility for its decision. So if you're using that algorithm and you're taking responsibility for that decision, you need to understand how it's arrived at it, or you need to be reassured that someone else who's an expert knows how it's doing it. It was actually, I think it was, so the firm Gartner that actually created the term big data originally, they said that they wouldn't use any AI tools in their management because AI could not take responsibility for decisions. And it's, yeah, it's an interesting field that is, yeah, not as well developed as it should be because it's not commercially valuable enough yet. Yeah.
Yes.
Yeah.
Any more? Yeah, you're itching there, I can see.
I recently read something about the evolution of AI. So we are at the doorstep of starting with instructive AI,
Mm.
and where the final of the five would be the innovative AI. So, but considering that we don't run the experiments with the black holes and the galaxies, so how can that ever really, we are amassing data, having new questions, but where are the answers?
Yeah, so I think for AI to provide innovation in astrophysics, it has to spot patterns that we haven't seen. Because when we see the patterns, we can't change the experiment, but what we can do is we can evolve our models to include that same pattern, right? And that's actually how a lot of the physical models that underlie astrophysics came into being in the first place. So certainly, I think in astrophysics, the innovation will come from that pattern recognition, or just speeding up analysis so fast that it allows us to innovate faster. Because innovation is not simply about just providing the answer, it's about providing the mechanism for getting to the answer. Yeah.
One very different questions. You said at the beginning that the headquarters are close to public. Is there maybe in the future a public interface?
Sorry, which one's public? Sorry,
the SKO.
Oh, in terms of visiting it. So yeah, so I think they have an open day once a year. At the moment, they're just not equipped for it, is the thing. So they have no, if you go to the Discovery Centre, there's a whole team there to run it, who are separate from the working observatory. And the SKAO, they don't have additional staff to do that. Also, it's just offices. It's not very exciting. It has a very nice coffee machine. But you joke, but it's actually because it has an international staff and the Italians insisted. Yeah, which is very beneficial. Yeah. Yeah, not quite there yet.
Any more questions? Any more on Zoom, Kevin?
No, chances, thanks.
No. At last on Monday then. Right.
It was just to come back to this data storage in space thing, because I think the anticipation was that it really was the future. It was at a satellite conference, and they were talking. So obviously the technology isn't in place yet, but I think the idea was that it's very costly to keep everything cold on Earth, and we've got so much data. They reckon that 90% of industry is dependent on satellite technology in one way or another. So
yeah, I mean, I suspect it might be something specific for the satellite industry or for sensitive data, because the
data transfer speeds.
The volume of storage you'd need to actually put into orbit, right? That launching something that heavy is very difficult. But then also to use the data, you'd have to put the processing up there as well. So yeah, so it's for very large data, I don't think it it's feasible, certainly not at the moment, but I can see scenarios where it would work.
But you are
Yeah.
correct that, you know, big data centers these days that Amazon's got, and Google's got, they use a huge amount of power to cool the computer.
Yeah.
Because they generate an enormous amount of heat. So obviously in the blackness of space, we radiate brilliantly. So it would make sense. The problem is getting the data to and from, which is where the fiber optics come in. Just when we have 1 square kilometers array, the fiber optics that you're using can't go that far because just of the volume of data coming off those dishes. Hence, you've got mini data centers sitting alongside all of the arrays, which then feeds the central data hub in those locations.
Got another question over here.
Sorry, possibly fatuous question, and nothing to do with astronomy either. But as you're the only person I've ever met who works in AI, I wondered if you think it'll ever achieve a singularity, and if Terminator will ever come true.
It's not something I lose sleep over. No, I don't. Yeah, I have to say I'm an AI optimist in the sense that I think that AI is going to do a lot that are very useful stuff. However, I think we're about to fall off a bit of a cliff in AI. So the big models that have caused, you know, all of the things that are happening recently, like ChatGPT, right? The GPT models, they're trained on the internet. They use the whole internet as their training data, but they've used it, right? So they were predicated, so OpenAI predicated their business model on being able to scale their models to become bigger and bigger and bigger. And that only works if you've got more and more and more data. And we don't, right? Like I said, they've used the entire internet. We don't have another internet just like, you know, waiting on a second server somewhere. So essentially for them to do something new at this point, they have to improve the algorithms. And that I think will happen. And it's going to be way more interesting than just scaling things up so they're bigger. But I think it's going to take longer than people expect. Yeah, it'll be much more incremental than the big jump that we've just seen. Yeah.
I think there'll be a lot more improvements in inclusive AI within things like mammograms and biomedical stuff, because of some of the stuff you're looking here, which is identifying.
So the personalized medicine stuff is really interesting. Yeah. There's a great group at the Christie working on it.
That
Yeah.
at the minute, yeah.
Yeah.
Does it mean we don't have to have our boobs washed anymore?
No, you'll still need to have the pictures taken. You'll have to take pictures.
Right. Okay. Has everyone asked the questions they want to
I'm
ask?
just going to drag this over here for a second because
Oh.
Annie's Whirlpool, and I thought that was quite an interesting image that somebody would have got given in Galaxy Zoo, and they've written, "I've got this bike, Rob. What are these all about?" And then somebody's come along and said, "Oh, that's a good question," and hence here it is.
Yeah.
What was the other bit that I was looking up? And going back to what you were saying around identifying new structures. Obviously, if all of a sudden the AI went, "Hang on, there's a new group that's over here," that would be a pattern that we'd be really interested in.
Exactly.
If the AI found it. Obviously, we have found almost all of the patterns unless we find some new stars that we've never seen.
Unless we find something new. Well, that's what the new data gives you.
Exactly.
Yeah.
And the amount of exoplanets, I'm surprised nobody started to.
Oh no, they are.
I thought they might be. I'll hand back to Susie.
Right. Thank you so much for a wonderful talk and for taking so many questions. We've been answering questions for nearly 35 minutes. So well done. Right.